Hi, so welcome all to the second robot session. In this session we will have three presentations, all related with perception and computer vision and image processing. And we will start by a presentation entitled Increasing Illumination Invariance of Surf Feature Detector Through Color Constancy. And it will be presented by Marcelo Petri. And we would like to thank Marcelo for fitting the slide into the screen. Thank you.
Good afternoon, I'm Marcelo, and in this presentation I'm going to talk about illumination changes, its impact on surf feature detection, and how to improve surf feature detector through color constancy. This presentation is organized as follows. So I'm going to start with an introduction and a very brief overview regarding image theory. Then I'm going to present our proposed methodology to extend surf, some experiments and results, and finally some conclusions. Features are described in the literature as salient image details whose characteristics significantly differs from its neighborhood. What they represent are not really relevant as long as they can be accurately localized through time. Features are used in several computer vision applications, including image classification, segmentation, object recognition, camera calibration, and motion estimation. Since features are used as main primitives of several algorithms, the quality of the final algorithm is limited by the quality of the feature detector. So some desired properties of feature detectors includes efficiency, distinctiveness, and repeatability. While efficiency is very related to the application domain, some applications can afford more time, but some applications cannot. The other two properties are very important for almost any application. As important as the feature ability to appear different from its neighborhood is its ability to be repeatedly identified in other images. However, the RGB image components are highly susceptible to light variations, which in turn causes variations in the feature detector response and then impacts on the robustness of the feature detector algorithm and in the final algorithm. Thus, it's very important to model those variations and understand their implications in the feature detection. So, assuming that a surface reflects light equally in all directions, I can model the intensity of a given pixel through the computation of this integral. If, however, I assume that the camera sensor responds to the light of a single wavelength, I can simplify the computation of this integral through the following relation, which is a relation between the surface reflectance and the light reflectance. One of the biggest problems of computer vision algorithms is that the object's apparent color varies according to the intensity and to the temperature of the scene illuminator. So, one of the most used models to deal with this kind of variations is the diagonal offset model, which describes the mathematical relation between two images, IC and IO, taken under different illumination conditions. And this is done through angular coefficients and through linear coefficients. Using this diagonal offset model, light variations can be classified into 5 distinct categories, according to the values of the angular and the linear coefficients. Well, the surf feature detector was designed to deal with scale and rotation invariance. It takes advantage of the determinant of the Asian matrix to detect blob-like structures. To simplify the computation of the second-order derivatives, surf uses takes use of Bloch-Spock filters. And to increase its efficiency, it combines it with integral images, making it very appealing for applications that require real-time, that requires real-time. In order to grant scale invariance, the algorithm computes the determinant of the Asian matrix using filters of several sizes, and then it compares the value of each determinant with its 26 neighbors. 9 from the upper scale, 9 from the bottom scale, and 8 from the same scale. The detector is, however, only partially invariant to illumination changes. Thus, it is important to understand which transformations have impact on the determinant of the Asian matrix and in which level. So here, we decided to verify the effects of the illumination change in surf responses. For that, we considered a single layered observed image, I/O, and using the central difference method, we approximated the computation of the second order derivative through a sum of intensity pixels. Sum of the intensity of the pixels. Now, considering that I/O has a corresponding image, IU, taken under unknown illumination conditions, and taking advantage of the diagonal offset model, I can model the relation between these two images. Now, substituting the equation 1 and the equation 2 into the determinant of the Asian matrix, I can come to the equation 3. And through this result, I can see that through the computation of the second order derivative, I can eliminate the effect of the linear coefficient beta. But, however, the effect of the angular coefficient is not eliminated in this response, and thus have a great impact on the final result of the determinant. Now that we know, now that we modeled the photometric variations, we designed a methodology to eliminate the effects of alpha in the surf response. For that, we took advantage of the local space average color. What is the local space average color? It is a biologically inspired theory designed by Ebner, which models how the brain achieves color constants. Ebner described in his work that it is possible to achieve an invariant descriptor, O, through the computation of second-order Gaussians. So in our algorithm, LSAC surf, we combine the illumination invariant properties of LSAC with the scale and rotation invariant of surf. For that, we compute LSAC descriptor for each pixel of the image and use that as working space to extract surf features. So, in order to measure the performance of our algorithm, we used the repeatability rate. The repeatability rate is the ratio between the number of features that were detected in all images of the same scene by the number of features detected in that specific image. In the next experiments, we compared the repeatability rate of the proposed algorithm with the original surf algorithm implemented in the OpenCV library. For that, we used 5 different image collections. 4 of these image collections have known transformations and were artificially created by us. While the real-world collection has 13 images of robotic soccer field. The artificially created collections have images of 1,000 objects in which each object has 9 different images with different coefficient values. So, in this first experiment, we desire to evaluate the effects of the linear coefficient in the repeatability rate. For that, we varied the linear coefficient 0.1 from minus to plus 20. And here in this image, we have some samples of 4 different objects that received this kind of transformation. The results here show us a high repeatability rate for both algorithms, the original surf and our proposed algorithm, which confirms the theoretical invariance of the algorithm to light intensity shift. Here in the second experiment, we wanted to measure the effects of the angular coefficient in the repeatability rate. For that, we varied the angular coefficient A from 0.5 to 2.0. And here we also have a sample of 4 images that received this kind of transformation. The results here, however, show us that the repeatability rate of a surf feature detector rapidly decreases according to the variation of the angular coefficient, while in our proposed algorithm, the repeatability rate keeps almost constant over these variations. And this result confirms the theoretical invariance of our algorithm to light intensity changes. In this third algorithm, we wanted to evaluate the effects of color light changes in the repeatability rate, and for that we used a dataset in which the voltage of the illumination lamps were varied, producing variations in the color temperature from 2175 to 3075 Kelvin. Here we have a sample of these transformations, and the results shows a very high repeatability rate for both algorithms. In a first hand, this result may seem surprising, but if we analyze it deeply, we can understand why this thing happened. Actually, this kind of variation this kind of transformation produces a variation in the color from yellow to white. Here, yellow to white, which is equivalent to a variation only in the blue component of the RGB color space. Well, the blue component is the component with less weight in the transformation from RGB to grayscale. So any variation here in the blue channel will have a very small impact on the final intensity of the image in grayscale. With that result, we designed another experiment in which we varied the color of the illuminant from blue to white. And for that, we varied the angular coefficients A and B from 0.2 to 1.0. So here I have a variation from blue to white, in which red and green were varied. In this case, I have a variation in the two components that have more weight on the grayscale intensity. So this is my results. As expected, surf feature detector, the repeatability of surf decreases very, very fast, while in our algorithm, it remains more constant and much, much higher, achieving not less than 65%. In this final experiment, we wanted to evaluate the effect of a noise and large real-world photometric variations. So for that, we mounted a camera in the robotic soccer field and took 13 images of a static scene in which we varied the light intensity and the state of the bulb lamps. Here we have some samples in which we can see that the room was only illuminated by these windows. And then we turned on some other lights, varied here the intensity, and etc. The results of these experiments show us that, again, our proposed algorithm has a much higher repeatability than the original feature detector. So, as conclusions, we presented a theoretical analysis that modeled the illumination changes and confirmed surf invariance to light intensity shift. We also demonstrated here the influence of the angular coefficient and its impact on the computation of the determinant of the Bayesian matrix. Our proposed algorithm was introduced as an extension of the original surf detector to increase its invariance to large photometric variations, using the local space average color descriptor as working space, and eliminating the effect of the angular coefficient. The results demonstrated a significant increase in the repeatability rate and confirmed the invariance, the theoretical invariance of the proposed algorithm. Thank you.
Thanks, and we have time for some questions. So, in the paper, you talk about other illumination invariant algorithms that try to minimize the effect of illumination on the results. You didn't compare with those methods. Do you have any?
No, I actually didn't compare with those methods because there was the algorithm was not available, and to implement those algorithms will require some time, and I couldn't afford at the time. But yeah, a future work should include a comparison with those algorithms, and.
I don't know if it was that the question before, but the time to process the surf or your algorithm, LS, yeah, surf is the same or the time?
No, actually it's not the same. Yeah, here we can see. I still use the regular surf detector here. The only difference is that I don't use the grayscale image as working space to extract features, but instead I use the LSAC descriptor, the invariant LSAC descriptor. So I have a previous step here, which is the computation of the descriptor. So I have the algorithm has a computational burden here in order to compute, and it varies according to the size of the image. Of course, bigger images will consume much more time. But It's not significant because here I also approximate the computation of the Gaussian using box plots and using integral images. So it's quite faster. And in this paper I don't present the results, but I have some results that show that it's not much longer.
Thanks again for your presentation. And we will move on to the second presentation, which is entitled Aerial Ball Perception Based on the Use of a Single Perspective Camera, which will be presented by João Silva.
Okay, so good afternoon. I'm João, and I will be presenting you this work on aerial ball detection. The focus of this paper is the detection of a ball in a robotic soccer scenario. I will start by doing a problem statement, introducing a small bit of the problem, then go through the detection part of the image detection part on both the methods that we use, then just introduce a small overview of how we then use the information, and finally present some comments and conclusions about this work. So, as I told you, this work is developed in the ambient or in the environment of robotic soccer, where this is a robot from the Cambada soccer team. And this is the robots which use this kind of approach. Just a small description of how all this works. The robots have as a main sensor an omnidirectional camera, which you can see the image here, and this is still the main sensor of the robot. So the vision process of this camera is the master of all the processing cycle of the agent, and so the work presented will be an add-on that must not, or should not at least, interfere with the main processes that are running in the robot. Saying that, limitations of this of the omnidirectional vision system. One of the main limitations is that although we see, or the robot can detect the things on a 360-degree span view, it cannot detect balls that go approximately more than 60 centimeters high. This means that the algorithms used in the omnidirectional camera actually take or assume that the ball is on the ground. So all the projections that are made assume the ball on the ground. But during a soccer game, even a robotic soccer game like this one, the ball inevitably goes into the air, especially when it is kicked toward the goal. So detecting the ball while it is in the air is an important skill, especially for the goalkeeper, which hopefully will have to intercept the ball to avoid a goal. So we will try to use a new camera to tackle this problem, a new camera which is applied in the robot in such a way that its focal axis is parallel to the ground. Why this this kind of approach and mounting the camera, because it simplifies a bit the problem, especially the mathematics behind the projections of the estimations of the position. So the objective of this new process that we are introducing on the robot computer, on the robot processor, is to have a fast and sufficiently accurate or satisfactorily accurate detection of the ball while it is in the air, so that we can have some information about those situations when we previously had none. So the total time available for everything that we use in our team is about 33 milliseconds. The camera, the main camera, works at 30 frames per second, and so everything must be done within this time window. This means that this new process, which will run in a free or a best effort scheduling on the processor, should not take longer than 10 to 12 milliseconds, and even though those times can be in the limit for the current system times. The ball to detect in this case is a standard size 5 FIFA ball, which has approximately 22 centimeters of diameter, and in each tournament it has a known predominant color, which we can take advantage of that prior knowledge. So focusing on the process itself, on the color segmentation part and all the image processing that we do, we start by getting the image from the camera. Each cycle we have a new image, and then we apply a color segmentation algorithm that classifies or looks or detects regions in the image that has the color of the ball, the main color of the ball. The segmentation is done by a raster scan, so line by line, and blobs of that particular color are built based on the Euclidean distance of the pixels that has the predefined color. These regions, these blobs that are created, are then analyzed in particularly in three characteristics: the solidity of the blobs, the minimum size, and relation between the width and the height of the blobs. That is why do we do that? Because we know that a ball, a round object, if it would be clearly segmented, we will have a perfect square around that ball. The dimensions should be more or less the same, both in width and in height. So we can simply ignore something that is a line of 1 or 2 pixels. It surely is not the ball. Or if it was the ball, well, it is not information enough for us to assume that it is. Afterwards, these blobs, or the blobs that actually pass this first evaluation, are used to create regions of interest on the image, so that these regions of interest are then analyzed by a global shape context that will then give us the final candidates of the ball, and those are the ones that will be evaluated to know the position of the possible ball. Here we have a screenshot of the one frame captured by the camera. As you can see, in this case we had a red ball over there, and purposely we placed several items with the same color of the ball around the scenario. This two-step analysis, you see the blue squares around the blobs. Each of the orange blobs of color are one candidate generated by the color segmentation, and so each of the squares are actually a region of the image, a region of interest, which will then go through the global shape context analysis. And in this case, in the end, that candidate was the only one that passed the second evaluation. In this case, it was the correct candidate, and it was really the ball. But what is this second step of the global shape context? Well, it's basically an analysis of a polar histogram, which is based on 3 metrics. So on the region of interest created, so on the image, on that small image that we have, a contour detection is performed, and that contour is analyzed through the polar histogram. Basically, the polar histogram is divided into layers and slices, something that is crudely represented in these schemes. And in this case, we have a perfect drawing, a perfect contour. And you can see here represented that the statistics of the contours in this case would fit a single layer. So this layer would have basically an average number of contour points that would be 100%. All the slices on that layer have the same amount of points of the contour, and it would be a perfect match, let's say, on a round shape. In this case, the contour points are divided into several layers, and thus the analysis of each layer would not be that good. It's important to say that this step of the global shape analysis always gives the best result, or returns the best result, the best layer. But that doesn't mean that those results are actually a round contour. So it returns the best result, the layer which has best results, and those results are also returned. And so then we have to see if the values, those values are actually good or not for us. And we analyze the ratio edge of the points on the ratio of edges points on the layer, the magnitude of the average and the standard deviation. It should be the standard deviation, which should be, well, much lower than the standard deviation, and if with a lesser magnitude, even better, and the coherence between the diameters that the polar histogram estimates and the previous analysis of the image candidate also evaluates. To test this evaluation, I've already showed you a screenshot of the scenario, but we try to test it with in several scenarios, with several balls, in several configurations, to try to discover which parameters were better for the results that we intend to. And as a short, some of the results are illustrated in this table. It's quite a large table, but should not be that hard to analyze. We have, in this case, 6 situations, 6 videos that we took from the camera, where the ball is being thrown in the direction of the camera or of the robot. 3 videos with a red ball, 3 videos with a yellow ball. And we tested the algorithm, particularly the global shape analysis, with, in this case, 2 and 3 layers. And after looking at the results, we clearly decided, okay, let's use 2 layers, because 3 layers have much worse results. And although in the case of the red ball, that would not be completely true, in the case of the yellow ball, we clearly see that using 3 layers yields a huge number of false positives. Now, in this case, we actually don't mind to lose a bit of precision and having less values. What is especially important is to minimize the number of false positives, as they can just pull away the robot from the real objective and go somewhere else and in this case, if it was the goalkeeper, go away from the goal, and the opposing team would score a goal. So in terms, we also tested the seed of the analysis of the polar histogram to start by in the center of the image or in the center of the contour. In this case, the results are not that different, but we find a bit more useful to use the image center because of the precision and recall relation that we got was slightly better in using the image center. What do we do then with this result? So after we have identified the ball in the image, we know where its position is in terms of pixels. We know that the center of the ball is in that pixel, which corresponds to a line and a column. And so through an evaluation of the size of the ball, we estimate the distance that the ball has from the camera, the distance away from the camera that the ball is. And why do we do that? We analyze the width of the ball. Because in this case, since we are only detecting aerial balls, we know that, well, at least in a robotic soccer game, only the ball will be in the air. So the ball will be totally visible. We will not have other the robots occluding some part of the ball. So the width of the ball should be its full width. And so, since we know its real size, 22 centimeters, we can easily estimate, knowing the parameters of intrinsic and extrinsic parameters of the camera, we can easily estimate the size or the distance that corresponds to a ball that size in pixels. To get this relation, we made a series of tests and captures to know and to measure what our algorithm actually measures. And placing the ball at different distances, we could estimate a polynomial, a third-degree polynomial, this red one here, to fit the sizes of the ball, the relation between the size in pixels and the distance of the ball. But we noticed that when the ball is huge in the image, it's very big, so when the ball is very close to the robot, the polynomial will not fit the points properly. Since the ball, when it gets to more than 100 pixels, is so close to the robot, once again, we can kind of reduce the need for precision, because a ball that size, if the robot thinks it is more to the side or to the center of the image, at that distance, it's close enough for the evaluation not to affect the decision, and so we use a linear approach for the last that last part, for the bigger sizes of the ball in the image. Saying that, the coordinates of the image, since the robot sees the ball and represents, in this case we represent the ball in X and in an X and Y system. In our case, the distance of the ball to the camera is directly the Y coordinate, so the front of the robot is actually the Y axis, and knowing that Y axis, we can estimate the pixel size, so the size that each pixel represents at the distance that the ball is, and thus from the displacement of the X of the ball center from the center of the image, we can estimate the side distance of the ball, which is the X coordinates. In here, we see here the evaluation of the position of the ball during a throw. So the ball was thrown at the camera. The camera is actually at the 0, 0. It's the center of the system. Thus, being this process that is complementary to the omnidirectional system, it's important to say that it was never intended to be used for stereoscopy in these robots. That, and something that we also noticed during the tests is that the ball sometimes comes at very high speeds, or most of the times comes at very high speeds, and the effects on the image is a raster that the ball just spreads along the image. It is not that round in most of the trajectory. The ball ceases to be that round, and thus sometimes, or in those conditions, we lose some efficiency in this approach, and thus we have less points on our trajectory. So one of the new approaches for future work that, well, it's actually being implemented right now with some preliminary results, is the use of a Kinect camera to take advantage of the depth information. Hopefully, in a brief future, we will be able to present some results of this new approach, which should be complementary to these ones. Thus, I finish my presentation, and will be quite happy to answer any doubt that you have.
Okay, we also have time for some questions, so. Yep.
Question concerning robotic soccer, we have basically we don't have still images, we have images in motion. Basically, we have a video. And so your approach doesn't use much of the previous information we have from previous frames in order to estimate what happens in future frames. Why is that, and how can you use the information from previous frames? Because in thinking in human terms, the ball is the object that is in motion in the field. Mm-hmm. And so that information is crucial, because it's very hard to get where is the ball in still images, but using the information from previous frames, typically it's quite more easy.
The first thing I know, if you are referring to using how do you call the detection of displacements on the image, vector something?
Using information from previous frames, because if you have 10 blobs in the next image, in the next frame, you may have 9 blobs in different positions, then you have 8, and typically exactly. The blob that is moving is the ball. Basically using a little bit of that information in order to improve the approach. Okay,
we don't use the movement detection algorithms in the image. We do use historical information from past balls. So in the moment that the agent this information is then fed to the agent, and in the moment that the agent accepts a ball candidate from the front vision, it actually knows that it started to see a ball on that front vision only after it loses the ball from the omni vision. From that point on, we actually select the ball candidates based on the position, on the last known position of the ball, so that if in one frame or in one given time the robot sees the ball in a position, in the next frame, if there is only one candidate on the opposite side, we just ignore and infer that that is not the ball. It could not move that far, and thus we ignore it. And we cease again to have information. We stay without information from the front vision, but we do not accept the false positives or the possible likely false positives in that situation. So although we don't follow the movement of the ball on the image, we actually use the history of the last positions of the ball to select the candidates that go to the agent.
My suggestion was more that to use the movement to help to because things that are still are false positives things that are moving are the ball, or is the ball. And the information from frame to frame may help a lot in order to reduce false positives, and not only before losing the ball in the omnidirectional vision. That's exactly what I was proposing, but my proposal was to use that during all the process, because if you are following a wrong ball, it may be very bad.
Yeah, exactly. So,
So you can use that throughout all the process. That was my main suggestion.
Well, that would also be an hypothesis, although here we have to consider that the robot also moves. Of course, we could try to estimate where all those candidates were, but that would imply that the agent would keep information on all the candidates that come. It would be an hypothesis. Still haven't explored that, no. Although we would have to get all the candidates, despite the ball and all the others, then backtrace all the positions to the amount of movement that the robot took, to then take them out. So in terms of the image processing itself, I'm not sure how we could do that without using those image movement detection, but it is doable if we put it on the agent side. It would be an approach to explore. Yeah.
Go to the last presentation of this session. Yes. Which is on human detection and tracking using a Kinect camera for an autonomous service robot. And it will be presented by Luís Ferreira.
So, good afternoon. My name is Luís Ferreira, and I'm going to present to you the paper with entitled Human Detection and Tracking using a Kinect camera for an autonomous service robot. At the time I wrote the paper for EPIA, I still call it work in development. So I didn't present that many results, and I didn't justify much of what I did. But right now the project is finished, at least for now, and I can now present much more information with more certainty. So, starting, this is going to be the structure for the presentation. I'll start by introducing some of the motivation behind the development of the project, state-of-the-art structure for the proposed solution, the part of people detection that summarizes in ROI segmentation, the regions of interest segmentation, and the ROI classification, and the people tracking capabilities of the system, along with some results and the conclusion. So the main motivation behind the development of this system was to create social robots, since a social robot is an autonomous robot that interacts and communicates with humans or other physical agents. Therefore, in order to communicate and in order to interact with persons, with people, we have to know, a robot has to know what is the people, what is a person in an environment, what it is, what is not. This allows for the creation of human-robot applications and service robots, such as the one you can see here in the image, who can, for example, help elderly people or disabled people in the house chores, or, for example, perform tours on a factory or in the store, perform autonomous tours. So, among the sensors most commonly used to perform people detection, we have the color cameras, thermal cameras, time-of-flight cameras, and the RGBD cameras. For this project, we use a Kinect camera, which is an RGBD camera capable of delivering color images and and also depth images, which are of great importance for the people detection part of the system. Among the techniques mostly used to perform this detection and classification, we can mainly divide this in two techniques: learning techniques, using a set classifier and a set of features to perform the classification, or template matching techniques that use a head-shoulder template because the head and the shoulders are the less deformable part of our body, or also full body templates. However, that depends more on the type of application that we are designing to. This is the main overview of the proposed system. So as you can see, we follow a consumer-producer model applying the Roche framework, and the Kinect delivers then color and depth images that are going to be used to that are going to be processed, which generate regions of interest from the depth image, and the color image is mainly used for the tracking capabilities of the system. Below, this part of the project it could not be finished in time, but there are some ideas on how to use the thermal imaging captured by another camera. So, as I said, we use the depth image to perform people detection. And normally analyzing a 3D space is much more costly than analyzing a 2D space. So one way to reduce this cost is to turn the 3D space into several 2D images or 2D planes, slices of the environment, that are more easily analyzed. In order to do this, we take this image, for example, and calculate its histograms. As you can see, the histogram provided by the depth image, which comes from the Kinect, is highly irregular, and even after a normalization, we can see that there are a lot of peaks, especially from around 4 or 5 meters ahead. The Kinect loses a lot of precision. Therefore, we first start by detecting the first order maximums, but because you can see there are a lot of peaks, then we take these first order maximums and detect the second order maximums from the first. So in fact, reducing the total number of maximums and therefore the total number of interest points to analyze in the image, and in this case in the histogram. So from these second order maximums, we perform a slicing of the histogram. And as you can see now from this example, with this image this histogram calculated from this image, you can see the slices that were calculated, and for each slice we are going to get a mask that was calculated by thresholding the levels in between each of the slices. And as you can see, because the two persons in the image are a little far distance from the camera, you can see that each one had its own mask and are present in different masks alongside with the other objects that were in the picture. So as you can see, this complete mask is not a region of interest. It also masks parts of the image that we do not care. We do not want to know where the floor is or what the floor is, in fact. Therefore, we know that the camera is mounted on top of the Combat@Home robot, a service robot. And we assume that the camera is parallel to the floor. Therefore, we can perform a cut in this mask in the plane above the floor plane, which allow us to separate the floor from the objects or the human candidates that are on top of it. For each of these candidates, even if there are more than one in one mask, we take the centroid of the unconnected objects, separated objects, and we use this centroid as a seed for a flood fill algorithm, which will allow us to retrieve one or more objects that are in each of the masks that you saw in the previous slide, resulting in the final regions of interest that only mask one object. Each region of interest only masks one object, one candidate. But as you can see, until now, the object detection of the system does not employ any human restrictions. We detect every type of object in the image without caring if it's human or not. So now that we have all of these regions of interest, we can start by discarding the ones that we know that cannot be a human. For example, by their proportion, by their area, and some other non-human related filters. So if we apply a proportion filter, you can see most of the rows in the back of the image are discarded. Second, by applying an area filter, you can see that this big ROI that was here no longer is. And these last two are especially efficient for smaller ROIs that are overlapped and which each center is close by. So you can see that the small ROIs that were mainly overlapped in this area and the little one over there disappeared, reducing the effective total number of ROIs in this image, for example, from 14 ROIs to 4, which will allow us to perform a faster processing or faster classification later. Initially, as I said, we use a template matching technique. And initially, we started using the templates used by other researchers, the actual templates. However, as you can see here, these are some of the contours in the corresponding distance transforms from people facing forward to the camera, backwards to the camera, and side to the camera. And as you can see, most of them, or some of them, present a shape that we would consider human, a round head, some shoulders. But as you can see in some of these images, like this one, and even some of the heads are missing, you can see that those are not shapes that we as humans would consider humans. So it doesn't make sense for we to design a template. It makes sense for the Kinect or to learn a template or create a template from images that the Kinect can actually see. And so using this pipeline, that's what we did, and we summed the distance transforms of each of the examples taken directly from the Kinect, perform a thresholding from the distance transform resulting, and apply a thinning algorithm alongside with a manual adjustment to create the final templates we used to perform the matching from frontal template, back templates, and side templates. Another problem with using monocular cameras to perform people detection is that these suffer from the perspective effect. And so an object close to the camera presents a bigger size, and an object further away from the camera presents a smaller size. Some researchers try to solve this by using an image pyramid, in which the image, or in our case the ROI, is going to be resampled through several sizes in order to allow for the same template to be matched at several distances. However, this approach didn't seem the most correct, since we can resize the template, and instead of using the template to perform a matching for each level of the pyramid, we perform a matching over only once for each region of interest instead of several times, which results in an enhanced performance. And furthermore, the template initially is converted to points, and therefore the resizing of the template does not employ any loss of precision as it happens when resampling images. The template matching is performed using the perfect match algorithm, as we've seen in the previous presentations. And this, as before, you can see that the perfect match algorithm is highly efficient, since it can present a solution in 20 iterations or even less. I haven't tested out to the maximum. But besides its efficiency that allows to test four templates in real time, it also allows for panning and rotation of the template. So as you can see here, this CT was created from the contours of the ROI, from this person. And as you can see, the template presents a very good fit, even slightly rotated. This is very important to find the best fit of the template over the image in order to get the best classification possible. Unfortunately, this perfect match algorithm, since it's a gradient descent uses a gradient descent algorithm, it's prone to encountering local minimums, and when the template is slided to a local minimum, it's hard for it to move away. Therefore, what we do, we assume the head is the topmost part of the body, and therefore we start the tour of the template at the top of the image in a specific column where the image is divided in several columns, and we started the tour in that point and starts going down slightly using the perfect match algorithm, and therefore finding the solution in a few frames and only rarely falling to local minimums. Only when the person, for example, is moving as their arms up and is covering part of the head. As for the the classification, we use a confidence level, and we calculate this confidence level by using a Gaussian distribution and using the error and the variance of this error. And as you can see here, the first two regions of interest are from people. I'm confirming that. And we can see that both the error and the variance of the matching in these two first rows is very low, generating a high confidence. However, in the last two that are not people, you can see that the error is not that much higher than previous. However, the variance is higher, it's very high, considering the previous variances, and therefore the last two rows present a low confidence. Because the system is capable of performing multiple people detection in the same frame, we have to have a way to be able to distinguish between these detections. And so, for example, when we are looking for Waldo in a crowd, we tend to look for the color in his clothes, the color in his pants, his shirt, also the hair and skin. So we take the similar approach, and for each of the persons found or encountered, detected in an image, we take examples from, we take the previous detections and compare it to current detections. So, for example, previously there was no one detected before. So the comparison matrix that you can see in this column is empty, or just one person, which is assigned the ID number 1. Next, another person steps in, and we see the comparison matrix growing. And finally, we can see that the second person also has a unique ID. The same thing as in the third. When the third person steps in and is detected, you can see that for each line of this matrix, there is always, or normally, one comparison value that is lower than the others, enabling the assignment of unique IDs to each user, even when they step out of the image and return. Also, because we use multiple templates, it's also possible to estimate the pose of the person. As you can see in the first image, the person is facing front to the camera, and among all templates are tested in all the rows, and so the one that achieves the highest confidence is the one that we assume the pose that we assume the person is in. So the image with the person facing front, the front template is the one that achieves the highest confidence. And also, as you can see, for example, in the last image, the person is facing right, and the template facing right is the one that achieves the highest confidence. In order to test the performance of the system, we did some tests in our field, in our university, and assigning 3 different values: a low, a high, and a low, medium, and a high value, to the 3 most important or most influential parameters of the system. We were able to create this rock curve that you can see here, and as you can see, we have a pretty steep curve where we have a high value for the true positive rate and a somewhat low value for the false positive rate that can later be optimized. But as you can see, the three best sets of parameters all have one thing in common: is that they, if you remember, the C variable. Oops, sorry. C variable controls the minimum consecutive detections above this S threshold. And so what this tells us is that even when the Kinect is standing still and the person is standing still, the detection of the Kinect, the borders of the object that the Kinect shows in the depth image are always kind of shaky, very irregular. So the system behaves better when we get it, give it time to perform several detections over the same object instead of enforcing a high confidence level in just one frame. As for the execution times for the system, in this last node that performs the classification and tracking requires for synchronized information from previous nodes, and therefore this can never outperform the slowest nodes than before. And as you can see, the color preprocessing node does not do much preprocessing, and it's fast. It can work at 30 frames per second. The depth node can only achieve the almost 19 frames per second, and therefore, after these messages are synchronized, the best that this last node can achieve is 15 frames per second. However, this is more than enough for real-time detection and tracking. And so, in conclusion, the system presented here presents real-time capabilities of detection and tracking of people. It presents a good performance, but it can be improved. There's a lot of room for improvement. It can perform detection up to 9 meters, which using a Kinect is really hard, taking in consideration that after 5-6 meters, the precision of the Kinect is really bad, and allows for the camera movement. So one of the things that people ask me is that there are already people detection systems. However, some of them, or many of them, work by background extraction. This system does not perform any background extraction, does not require any training. So you can point the camera to any place, move the camera, and it performs detection without the need of keeping the camera still. The template matching algorithm used allows for the use of multiple templates and the pan and tilt of the template, which is very important. And as I said, we use the perfect match algorithm also. And as far as we know, it's the first time it's been used for people detection or for people classification or the classification of templates in this manner, in this area. As for the people tracking capabilities of the system, you can see that can effectively estimate the pose and location of the person. As for the location, it requires other algorithms to be running on the robot, such as the one we saw before from Eurico. And because we use head shoulder template to perform the matching, if the matching has a high confidence, we know where the head of the person is. So if we want to take a log of the faces that we encountered along the way, we can do so without the use of additional algorithms that would also be heavy on the processor. This work has been presented alongside with other algorithms running in the Cambada at Home robot in the Robótica 2013, and it was awarded first place in the FreeBots Challenge at this competition. So for future work, it would be nice to be able to implement a more efficient method to analyze the depth image, enabling the increased speed over the overall system, since it's the depth preprocessing node that is slowing down the whole system. It would be interesting to have a better method to detect the limits of the person. For example, as I said, right now we detect the limits of the person with the contact with the feet, with the floor, by creating a cut slightly above the floor plane. Probably using the color camera, we can find a better way to perform this detection of the limits. For example, if I'm touching the table, depending on the distance of the camera, if the precision is low, the table would eventually be considered the same as me because we have a connection by my hand. And so, as for the classification, it wouldn't be too hard to adapt the shape of the template over time. Since we turn the template into points, we can easily adapt the shape of the template for each of the persons detected. And also, to perform the classification using not only the contour of the ROI, but also the data inside that ROI. So we know a person can't be flat. We know a person has to have certain different depths in its content. So instead of using just the contour of the ROI, use the inside of the ROI. Finally, in the people tracking capabilities of the system, it would be nice to have a facial recognition system using thermal imaging. Since we got around to investigate how this could be done, and there are a lot of works and really interesting and promising works that allow for facial recognition using thermal imaging. So I think I may have time to show one video. I think we have. Okay. Okay. Just a quick peek at some of the capabilities of the system. So just quickly, just to explain. Whoops, sorry. This is not on the right screen. Okay. So up here we have the unique ID of the person detected, the pose of the person, since a pipe, the person is facing forward. As you can see, the symbols will change as the person changes its pose. The confidence level for this current frame or for this current detection, and the location of the person. As for the pink dot, it is used for it is used for the manual location, manual pointing of the position of a person in the image, so for testing purposes. So it kind of missed there for a while. As you can see, this user was user number 2, and this user is now user number 3. Even after Eurico here leaves the image, false positive there, leaves the image and re-enters the image, when he is redetected, it is still user number 2 and still user number 3. And as you can see, the pose estimation, sometimes pointing to the left, to the right, for example, is facing right in this position. And so as you can see, you can do a you can get the real region of interest in the image. So.
The range, you spoke that it can be applied up to 9 meters, but some of the interactions with the robot happen at a very close distance. Can you still use this at a very close distance?
The problem is the Kinect is mounted on top of the Cambada Tome, so the robot is approximately this high. So the interaction with the person can't be too close to the robot, because we need to have full vision of the shoulders and head. So if I come too close to the camera, eventually my head will be cut off and I will not be considered a person. So we need at least 1.5 meters, if I'm not mistaken, a distance to the robot. But as I said, beyond the 4 or 5 meters, the precision of the Kinect is really, really bad. And it's hard to detect people at 9 meters. If the person is detected before the 9 meters and goes up to the 9 meters, the system is capable of continuing the tracking. But perform tracking at 9 meters is kind of hard. So it is to perform below 1.5 meters.
So if you want to interact with the people and to give some object to the people, then you would have a problem.
Right now, yes, because the service robot, the Cambada Tome, is not complete yet. So when the robot is complete, he will be able to rise. He will have a spine, and as he rises, also the camera will rise, and it will enable the interaction of the person, which will the robot will also have hands and arms one day.
So we still have time for some questions.
I don't know if you have answered to this question that I will make, but how do you classify the user? How you identify user 1 and user 3? Sorry, but maybe...
No problem. No, I advanced maybe a little too fast because I had a lot to show, I think. But using user 1, okay, the ID assignment starts in 1 and goes growing. So using performing Instagram comparison, for example, I am wearing a blue shirt. The program does not know what is blue, but it does know what were the channels mostly used for me, for example. If I were to compare against that person using a lot of white, the comparison between them would generate a high level. I don't know if you can see the levels here, but there are, for example, in here, there are 2 people previously detected and 2 people in the image. So one frame, the next frame. As you can see, one of the comparisons from the first ROI and the first tracking generates a high level. As for the first ROI and the second tracking generates a low error. So using these lower errors, you can compare, you can associate a previously detected person to a current ROI in the image.
Okay, that is for short memory, because if the user appears the next day.
Yes. This is only for short interactions.
Okay.
Even in the during testings, we tested the robot in a corridor, and so in the beginning of the corridor, we had some lighting conditions. At the end of the corridor, it was much darker. So even in that situation, it requires some more research on what channels to use, what values to use for the comparison, because some lighting conditions also affect the effectiveness of the tracking.
Okay, thanks.
Any more questions? So I think we should thank. And this was the last presentation of this iRobot session. Next we will have at 6 p.m. In this room the EPIA meeting, in which you should not discuss iRobot topics. But then we will have dinner, and the bus for the dinner will be at 7:45 at Terceira Mar Hotel. And during the dinner, I hope that we will have lots of discussions on iRobot and EPIA topics. And tomorrow we will have the Kenneth Stanley at 9, and then just after the invited speaker and the coffee break, we will have the next iRobot session. I hope you can see them there. Thank you.